My name is Sankirtan and I'm from CSCF section, and my topic for the AET is error correcting codes in space communication. Introduction to error correcting codes in space communication. Error correcting codes are essential for reliable data transmission in space environments. Error correcting codes play a crucial role in ensuring reliable communication in space exploration. Error correcting codes are techniques used to detect and correct errors that occur during data transmission or storage. They work by adding redun- redundancy to the data, allowing errors to be identified and corrected. Why are error correcting codes needed in space communication? Space communication involves transmitting data over vast distances, making it prone to errors caused by noise and interference, signal attenuation, radiation and cosmic rays, equipment malfunction. Error correcting codes help ensure that data is transmitted accurately and reliably. They help detect and correct errors caused by noise and signal degradation. This presentation explores their types and applications and importance in space missions. The need for error correction in space. Space communication channels are prone to high levels of noise and signal loss. The need for error communication in space communication is a challenging task due to vast distances involved and the harsh environment of space. Errors can occur due to various factors, making error correction crucial for reliable communication. Some challenges in space communication are signal attenuation. Signals weaken within distance, making them susceptible to noise and interference. Cosmic radiation, solar flares, and other sources of noise can corrupt data. Radiation can cause bit flips, errors, and even permanent damage to electronics. Hardware failures or software bugs can lead to data corruption. In summary, error correction is essential in space communication due to the challenges posed by space environment and the consequences of errors. By using error correcting codes, space agencies and organizations can ensure reliable communication, protect data, and achieve mission success. Basic concepts for error correcting codes. Error correcting codes add redundancy to original data for error detection and correction. The basic concepts are error correcting codes are used to detect and correct errors that occur during data transmission or storage. Here are some basic concepts. Redundancy. Redundancy is the addition of extra bits to the data to enable error detection and correction. Redundancy is achieved by adding partiality bits and check bits or redundant data. Code distance. Code distance is the minimum number of bits that must be changed to transform one valid code word into another. Code distance determines the error detection and correction capabilities of a code. Hamming distance. Hamming distance is the number of positions at which two code words differ. Hamming distance is used to measure the similarity between code words. Error detection and correction. Error detection is the process of detecting errors in the received data. Error correction is the process of correcting errors in the received data. Error detection and correction are achieved using redundancy and code distance. Types of errors. Single bit error, an error that occurs in a single bit. Multiple bit error, an error that occurs in multiple bits. Burst error, an error that occurs in sequence of bits. Code parameters. Code length, the total number of bits in a code word. Data length, the number of data bits in a code word. Redundancy, the number of redundant bits in the code word and the ratio of data bits in code words. These concepts form the foundation of error correcting codes and are used to design and analyze error correcting codes. Types of error correcting codes. Block codes process fixed chain blocks of data. Block codes divides data into fixed length blocks and add redundancy to each block. Example Hamming codes, Reed's hormone codes, and BCH codes. Correlational codes encode data in continuous system using a sliding window approach. Example Viterbi codes, and turbo codes. Modern codes often combine features of both enhanced performance. These categories are not mutually exclusive, and many codes can be classified under multiple categories. Block codes overview. Block codes, including popular examples like Hamming, Reed-Solomon, and BCH codes. Block codes are the type of error-correcting code that divides data into fixed-length blocks and add redundancy to each block. Fixed block length. Data is divided into blocks of fixed length. Each block contains redundant bits of for error detection and correction. The ratio of data bits to block length. Types of block codes: Hamming codes, single error correcting codes with minimum distance of 3. Multiple error Reed-Solomon codes, multiple error correcting codes with a high code distance. BCH codes, multiple error correcting codes with a flexible code length and distance. Block code parameters: the total number of bits in a block. Redundancy: the number of redundant bits in a block. Advantages are: block codes are relatively simple to implement and decode. Block codes can correct multiple errors depending on the code design. Block codes are used in data storage systems such as hard drives and solid state drives. And block codes are used in communication systems such as satellite communications and wireless communications. They are widely used for error detection and correction in digital communication. Block codes are especially useful for correcting burst errors in space. Hamming codes in space communication. Hamming codes can detect and correct single-bit errors efficiently. Hamming codes are a type of error-correcting codes used in space communication to detect and correct single-bit errors. Why Hamming codes are used? They are a simple implementation. Hamming codes are relatively simple to implement and decode, making them suitable for space communication systems with limited computational resources. Hamming codes can correct single bit errors which are common in space communication due to radiation and other forms of inheritance. Inference. Applications in space communication. NASA's Voyager mission. Hamming codes were used in the Voyager 1 and 2 missions to ensure reliable communication with Earth. Hamming codes are used in satellite communication systems to correct errors caused by single attenuation and inference. Hamming codes are used in various space exploration missions such as Mars Curiosity rover and ensure reliable communication with the Earth. Hamming codes provides high reliability in space communication systems, ensuring that the data is transmitted accurately. Hamming codes have low complexity, making them suitable for implementation and space communication systems within limited resources. There are some limitations. Hamming codes can only correct single bit errors, making them less effective in environments with high error rates. Hamming codes have a limited code distance, which can make them less effective in correcting multiple errors. Their limitations make them less suitable for noise and space channels. Reed-Solomon codes. Reed-Solomon codes are effective against burst errors common in space signals. Reed-Solomon codes, they are used in deep space communication, and Reed-Solomon codes are a family of error-correcting codes. They are widely used in digital communication systems, including space communication, CDs, DVDs, or queues. Reed-Solomon codes can correct multiple errors, making them suitable for applications with higher error rates. Reed-Solomon codes are the type of block codes dividing data into fixed-length blocks. Reed-Solomon codes operate on symbols rather than individual bits. Applications. Reed-Solomon codes are used in many communication systems, including NASA's Voyager mission and Mars Curiosity rover. Reed-Solomon codes are used in CDs, DVDs to correct errors caused by scratches or defects. Reed-Solomon codes are used in QR codes to provide error correction and redundancy. Advantages. Reed-Solomon codes can correct multiple errors, making them suitable for applications with higher error rates. Reed-Solomon codes can have efficient encoding and decoding algorithms, making them suitable for real-time applications. Their ability to correct multiple symbols errors make them highly valuable. BCH codes. BCH codes are a class of powerful cyclic errors. Bose-Chaudhary BCH codes are a class of powerful cyclic error correction codes. BCH codes are the family of cyclic error correcting codes that are widely used in digital communication systems. The key characteristics are BCH codes can correct multiple errors, making them suitable for applications with high error rates. And BCH codes are the type of cyclic code, meaning that they can be represented by a cyclic polynomial. BCH codes are used in various communication systems for their robustness. Convolutional codes. Convolutional codes process data using shift registers and generate redundant bits. They are suitable for real-time error correction in continuous data streams. Turbo codes and LDPC codes. Turbo codes combine multiple convolutional codes with iterative decoding for high efficiency. LDPC, low density parity check codes, offer near Shannon limit performance. These advanced codes are increasingly used in modern space missions. Space missions using error correction. The Voyager mission utilized Reed-Solomon codes for deep space data transmission. The Hubble Space Telescope employs error correcting codes for image data integrity. Mars rover rely on convolutional and turbo codes to transmit scientific data. Challenges in space error correction. Limited bandwidth requires efficient code schemes with minimal redundancy. Deep space environments pose unpredictable noise levels, complicating error correction. Recent advances in space coding. Development of LDPC and turbo codes has improved data rates and reliability. Adaptive coding techniques respond dynamically to changing channel conditions. Future directions in space error correction. Integration of machine learning algorithms for adaptive error correction. Exploration of hybrid coding schemes combining multiple coding strategies. Focuses on reducing power consumption and decoding latency. Impact on space mission success. Robust error correction enhances the success rate of deep space exploration. It ensures critical scientific data is received accurately on Earth. Reliability communication systems enable more complex and longer missions. Summary of the key points. Error correcting codes are vital for maintaining data integrity in space. Various codes like Reed-Solomon, BCH, Turbo, and LDPC serve different needs. Conclusion. Conclusion for the topic. Effective error correction is fundamental. Effective error correcting codes play a crucial role in ensuring reliable communication in space exploration and other digital communication systems. Hamming codes, Reed-Solomon codes, and BCH code are some of the most widely used error correcting codes. And as technology continues to advance, the importance of error correcting codes will only continue to grow, enabling us to explore further and push the boundaries of human knowledge. Future missions will benefit more from the sophisticated and efficient code techniques. These are the references. Thank you.